好，谢谢。他们忘记带走了，你先把他们收起来好。这个日历有办法秀在现在的画面上吗？
这个
对。因为我想拉过去，好像这也不能拉这样。
对，因为它就只会显示在这边。
好吧，那没有，我用讲好了哈。好，那各位同学，我跟大家讲一下我们接下来这一个月的课程的 schedule， 好，就是我们怎么安排这个月的课程，包含大家应该已经有在 eCourse 上面有看到我们的公告，就是我们这学期的期中考呢会在10月的最后一周的10月30号，好，那我们会在当天期中考，好，那期中考的内容呢就会是在我们10月30号这一周之前的上课的所有的内容，包含我们实体上课，还有我们提供的这个预录的影片，好，那些都会是我们期中考的范围。所以一直到10月30号，等于是23号那周的上课的内容，就是我们期中考的范围。那我们期中考的题目呢，好，会跟之前比较不一样一点。好，我们这次呢会全部都用选择题的方式。好，那这个选择题呢会从 Notebook LM 里面的我们课程教材里面的出题，好，用 AI 来帮我们做出题这样。所以我们上次有跟同学介绍怎么样用 Notebook LM 来观看每周的英文的录影的影片。好，那同学把这个影片输进去之后呢，就可以产生各式各样的考试的测验题，好，还有我们学习卡的一些问答的内容。那我们这次的期中考就会从这个 Notebook LM 里面帮我们出的所有的题目里面去选一些题目出来，当做期中考的内容。好，所以同学如果希望期中考有好的表现的话，欢迎大家能够多多使用这些 AI 工具，协助同学们了解这学期英文上课的内容。好，那刚有讲到就是我们期中考的下一周，好，也就是11月6号当天，好，也就是10月30号的下一周上课，就是我们多媒体创意发想的时候。好，所以同学从现在开始就可以准备当天创意发想的内容。那我们的多媒体创意发想呢，大概每一位同学3到5分钟左右，好，然后提一下你有什么新的概念，能够把多媒体或者是相关的智慧技术能够应用到长者的不论是生活或人权相关的应用里面，好，协助他们做事情更便利等等的。好，那我们就用一周11月6号那一天的时间，好，让同学来做一个创意发想。那这个创意发想很重要啊，因为接下来它就会变成我们的 final project 的题目。好，所以在当天同学们听完所有同学的创意发想之后，好，那如果你对其他同学的创意发想有兴趣，就可以形成一个2到5人的组别，好，当成是我们 final project 的题目。好，那当然可能有些同学的创意发想是这个天马行空啊，好，这个想法很不错，但是可能要10年之后这个技术才能落地，那它就比较不适合当成是我们这学期 final project 的题目。好，所以同学在发想的时候可能要兼顾这个设想或设计的创意性、便利性，还有它落地的可能性。那甚至呢，同学甚至可以在这个 Google 上面多找找看，好，有没有相关你的 idea 别人已经做出来了，好，可以做一些 survey 这样。那另外呢，在10月30号的前一周，好，就是10月23号， 那老师那周参加这个国际的会议，好，所以我们那周也会用这个影片的方式来上课，好，所以等于是我们从10月23、10月30还有11月6号，好，先跟同学说明一下我们接下来几周上课的情形，好，看大家有没有什么问题，对于我们的期中考还有这个多媒体创意发想。英文，对，好，那这个请大家好好准备。那如果你真的觉得英文太困难，或者是太痛苦，或者是讲不清楚的话，你也可以用中文。好，那我们用英文 present 的同学会有额外的加分。好，那我想这个同学难得会有一个机会啊，用英文来做一个简报，而且其实只有3到5分钟，大家应该要好好把握我们这次做英文 oral presentation 的机会。好，还有没有其他问题？好，没有的话我们就开始上课喽。Today we are going to introduce Unit 3, Digital Image Processing. In this unit, we will see several image processing methods, such as index color algorithm, deterring algorithm, and how we process image content. For example, we have pixel-based processing, or we have spatial processing, such as convolution. And next, we will jump to another topic, image sampling and interpolation, especially if we want to change the resolution or aspect ratio of the images. We will introduce several resampling and interpolation methods. Finally, we will see image compression method. So we have seen several methods before, but here we will focus on a very common method, LZW compression, which is very common for painters. Okay, so actually you can see the options in a lot of applications applying LZW compression. Okay, so for digital image type, if you take a picture with your camera, then you need to save this content into your device. So you may have several different choices on which type to store this photo. For example, BMap. Okay, so you will see the file extension .bmp or .gif. Okay, so BMap is what we call raw data because it just follows the RGB channel. For each channel, we use 8-bit to represent the image content. So totally for BMap files, we have 3 channels. So we use 24 bits color depth to represent these images. Of course, we have another type of images which using 32-bit. So you can see compared to 32 to 24, we have additional 8-bit for one additional channel. We call that alpha channel. The alpha channel is used to present the transparency. So maybe for like PowerPoint or words, you may see the options to draw the score bar. Then you can adjust the transparency of the images. Maybe for the white background, if you adjust the transparency to 100%, then it becomes totally transparent. Okay, so in that case, actually you are using 32-bit of the file format of BMap. All right, then you may see the options wrong length encoding in the painters. Okay, so we have seen this compression method before. Or actually you can apply compression or no compression when you save the BMap file. Okay, the second file, the GIF, actually is kind of animation. So the full name is Graphics Interchange Format. When you are browsing the website, you may see the GIF a lot because sometimes it's used for the icon or maybe the display of several images, so you can see kind of animations using GIF files. Okay, so for G files, it applies LZW compression. So we will introduce this part later in this unit. All right. I believe in next unit we will see the mechanism of progressive downloading or interlapse. The mechanism is how to display such image content when you are browsing a website. Okay, so you may see different mode, progressive mode or interlapse mode. That's for high resolution images. Okay, so maybe due to the limitation of transmission of the network, we can still see some part of the images under progressive downloading. All right, next part is JPEG. We have seen how to apply DCT to like transform the spatial domain to fluid domain to represent the data. Then we can apply JPEG compression algorithm to like reduce the size of the images. Next one, I'm not sure if you have used this before. .png, portable network graphics. Have you used this file before? Okay, where did you use it? In what circumstance you will save your file to .png? That's right. Sometimes when you are downloading images from the website, the default file format is already .png. Okay, so maybe when you in the master degree and you need to write your master thesis, sometimes when you're using LaTeX to write your master thesis, we always use the file PNG as the file extension. We are not using JPEG or BMap. When you are using LaTeX to write your master thesis, we always use .png. So you will see this a lot when you study your master degree. Okay, other than this method, actually we have a very simple file format which is called indexed colors. Okay, so for indexed color, that's used for very limited storage or very limited devices. So it contains a color table which is called palette. Okay, so how to reduce all kinds of colors using palette to represent these colors. We will see this later. Okay, next let's see color quantization. Okay, so we have learned the concept of quantization in Unit 1, right? To represent a range of real numbers by the partition or interval. And we can define the Q to define the interval. And all values within this range will be represented by the middle value of this range. That's what we have learned in Unit 1 for quantization. For color images, the process of reducing number of colors we call color quantization. Because the possible colors is more than 70 million. Okay, so we have a lot of possible colors. How to reduce all the color numbers? We can apply color quantization. Okay, so this method is called indexed colors. It's a technique to manage digital image color in a limited fashion. Okay, so maybe we can see the example in the right-hand side. Okay. Originally, if we use the full color, so 17 million of colors, every colors you can use within these RGB images, then we can see the image of the cat, the color looks very smooth. However, if you have very limited devices, very limited memory storage or computational resources, then you are allowed to use only 16 colors, just like this. 1, 2, 3, 4 to 16. Okay. How to use only 16 colors to represent the same cat image? Okay, so you can see this is the final results of indexed colors use only 16 colors. So apparently we can find some artifacts. For example, we see a lot of color patches here. Okay, light gray, dark gray, and even darker gray colors. But you can see from the results, it's look reasonably good because we only use 16 of colors, and the content is comparable to the original content. Okay, so let's see how we apply color compensation if we are allowed to use only limited number of colors. Okay, the first thing is we need to decide a bit depth of n, and that reduce the bit depth to b. So originally, if we use 8-bit, then for limited colors such as 16, we may change the bit depth from n to b. Okay, so this allows us to use original 2 to the power of n colors and reduce to 2 to the power of b colors. Okay, this is the first thing we need to define, such as we use 16 colors. Okay, then next we have 3 steps for color compensation. The first step is to determine the actual range and number of colors used in the original image. Okay, so even though we have all the possible colors, more than 70 million, but given input images, we actually not use all of these colors. So we need to determine the actual range, how many colors we are using in the cat image. For example, 1 million or 2 million or something. Okay, next, the second step is to choose 2 to the power of b colors. Then we can use such colors to represent the original image. Okay, for example, for these butterfly images, if we choose 12 colors, okay, so we may choose green, orange, yellow, or black and white. Okay, because you can see these colors appears a lot in this butterfly image. So we need to choose 2 to the power of b colors as the index color. Finally, we need to map the original colors to the index color, what we choose in step 2. Okay, so we can replace the original colors by the index color. Okay, so let's see the example. Okay, so in this case, if we choose a bit of our colors, then we can build a table like this. Okay, we have 256 different colors, so we can use 0, 1, 2 as the index of these colors, and then it can map to different colors. Okay, so let's see how we map such colors. To map the original colors to the table, or what we call palette, we can find the most similar colors using the minimum mean square distance. Okay, so imagine you choose, for example, 12 colors in this table. So you have the RGB values for these 12 colors. And then you can calculate the original colors to see what is R minus R, G minus G, and B minus B for the original color channels in the index color channels to calculate the minimum distance. Okay, so take this color for example. If this color we have its RGB values, right? So if this value equals a very large number here, okay, then we can calculate the distance to the 12 colors we have chosen. In this case, we chose 256. So maybe this Okay, so maybe we have the first color, the second color, the third color, and then we can use this value to calculate the distance to all index colors to see which one has the shortest distance. And then we will map that color to the index. Okay, so you can see when we store the colors, we are not storing the actual colors. Instead, we store the index of the colors. For example, once we have the color, so this is 700 to 100 something. Okay, so once we have such colors, then we can compare on which entry we have the minimum distance. Okay, so in this case, you can see once you calculate the distance from this value to all this palette value, then we can see the shortest distance is closest, which is closest to the index 254. Because you can see this number is very close to this number. Okay, so if you calculate the distance from this value to all these entries, and you can find the minimum distance, this one is closest to this one. Okay, so in this case, we will replace the original colors by the color in the palette. So we store the index. The index is 254. So in the index colors, so we just store 254 in this location. Because we know once we have this lookup table, we have the index 254, then we can see we can use this entry to look up in the table. Its color is this one. Okay. So if you imagine this color is the index colors, then we can replace the original images to replace its color one by one. Once you calculate the minimum square distance, then you can replace the original images to the index of the palette. Okay. Once you have the index by this palette, we can see what is the actual value for the index color. All right, so let's try this example. So we have a palette in the left-hand side. Okay, in this case, we only have 8 different colors. So the index will be 0, 1, 2, 3, 7. And from the table, we can see for each entry, it mapped to 8 actual colors. We have selected as the index color 0, 23, 67, and something. Okay, and then try yourself. Once we have the image like this, okay, how we apply the index color using this palette to represent this table. Okay, so you need to answer what is this color and what's the stored value for this image. Okay, anyone can provide the answer? I will give you 1 extra point. All right, maybe I would like to invite someone to summarize this message in Chinese for everyone. 1 extra point. Could you summarize the message in Chinese?
就是先把很多颜色缩减成就是重要的几个颜色，然后接着就要把原本原始的颜色，然后靠这个命的那个公式，然后去看说带哪个值最小，带的比较小的那个值就把它对应带到那个上面那个颜色，然后它的值就是比如说900，110它值就是250。
All right. So, do you get the point of this method? in Chinese? Alright, so are you able to answer this question? One extra point. Please write your answer on the blackboard. Alright, we have the original image 2 by 2, and we already have the palette which contains 8 different colors. Right, thank you. So let's see. Once we have the actual color 62333, what is the minimal distance of the color in the palette? If you calculate the distance from this one to 0, this one to 23, and all these 8 entries, I believe the shortest distance will be this one, right? If you use AA1T2 minus 6233, then the distance will be the minimal compared this one to other entries. Okay, so in this case, once you can find the minimal colors with the minimal distance, then its colors will be 88122. Okay, so this color will replace by the actual color using the existing colors in the palette. Okay, so its color will be here, A will be 88122. Okay, and then when we save these images, we are not actually save these values. Instead, we save the index of the palette. So the index of 88122 is 5. Okay, so when we save these images, actually we only save 5, the index number in this location A. Okay, so maybe you can try yourself for other pixel. For example, this value is so large, so maybe the shortest distance is the last one. Okay, so this color will be replaced by this color. Okay, so you can see from your answer, okay, it's 2 million something. Okay, and the index will be 7. Okay, so the answer is correct. Thank you. I'll go to TA after class. All right, so let's review this color quantization method again. The first thing is to determine the actual color. How many colors appearing in these original images? And then we need to choose index color in the palette. So we may choose 2 to be different colors. Then we can calculate the mapping, how to map the actual color to the index color. And then we can replace the original colors by the colors in the palette and save its index in the file format. So next, I would like to introduce several algorithms for step 2, because for step 2, we only talk about we need to choose 2 to the power of B colors, but we don't know how to choose such colors. For example, for this butterfly image, why we choose these 12 colors? How to choose it? Okay. So next, I would like to introduce several algorithms to help us determine this index color. Okay, the first algorithm is called popularity algorithm. It's the simplest way to achieve a function from b times n to b times of b. So we can only choose the most often colors Okay, if it appears most often, then we can choose it. For example, you can have the calculation or statistics how many colors of red appear in these images. So it will be easy, right? Once you have color histogram, then you can calculate the occurrence of all colors. Then we just choose the first 12 colors that appear the most. Okay, that's what we call popularity algorithm. Okay, you can see this algorithm is reasonable because once you choose the color that appears most often, then when we transform the actual color to index color, the color should not change dramatically. But we still have the artifacts of this algorithm. For example, from this image, you can see the color appears most often maybe blue, white, or brown. Okay, but we have some text in the right bottom corners, which is red. Okay, so by popularity algorithm, you can see the color red is not likely to be selected in the index color. So after color quantization, maybe the color of the red text will be replaced by maybe blue, white, or brown, but it's actually not red. Okay, so that's the drawback of this method. Because when this color appears not that often, maybe for the index color, the color will change significantly. Okay, next let's do this exercise. If we apply popularity algorithm to this 24-bit color image A to obtain a 2-bit index color B. Okay, the first question, what is the index table of the image? B, what is the indexed image B? Okay, so the idea is to choose 2-bit index image by popularity algorithm. Okay, let's try this exercise. Maybe you can determine if we have 2-bit index colors, how many colors will be in the index table? 4, right? I can see your fingers. Okay, so how to choose such 4 colors by popularity algorithm? Okay, do you want to try the first question? 1 extra point if your answer is correct. Please write down your answer here. So for 2-bit index colors, and we need to choose 4 colors. Okay, so we have the palette indexed by 0, 1, 2, 3, and then we choose 15, 46, 72, and 88. Okay, thank you. Let's verify her answer. Why to choose 15? Because from image A, you can see 15 appears twice. This location and this location and this location. Okay, so it appears 3 times. Okay, and then he choose 46. Okay, 46, 1, 2, 3. Okay, and then 72, 1, 2. All right, and then 88, 1, 2. Okay, you can see other colors only appear once. Okay, at least 88 appears twice. Okay, so from the popularity algorithm, we choose the colors appears the most. Okay, so that's the reason we choose these 4 colors. Okay, once we build the palette, so what is the index image B that can represent image A? Anyone? Okay, please. All right. So remember when we transform the actual image to index image, that will be the step 3. We need to calculate the mapping. So the mapping is based on the minimal squared distance of the colors. Okay, so let's see for the first location. The first location is 95. Okay, so what is this answer? 3. All right. Okay. So if we calculate the distance from 95 to these 4 colors, then we can see the minimal squared distance will be 95 to 88, right? Okay, so the indexed images, the first location will be 3. Okay, so maybe we can check quickly. For 88, it will be 3. Okay, and then for 72, it will be 2, right? Okay, for this location, actually it's appear in the index 2, but you're writing 3 here. Okay, just a little mistake. Okay, and let's see, 0 and which one is closer? This one. Okay, so 0, 0, 0, 0, right? 1. Okay, let's see. The distance from 32 to 50 is, okay, 17. Okay, so this one is closer, right? Okay, so 0, 1, 0, 0. Okay, so maybe you can verify yourself. If you calculate the distance from the actual value to the colors in the palette, then you can retrieve the minimum distance by its index and fold the index image P. Okay, so this is the first algorithm, popularity algorithm. It's very easy. You just get the colors that appears most often. Okay, but we have the drawback because we cannot represent the red color very well. So let's see another algorithm, uniform partition algorithm. Okay, let's see the steps. The first step is to find the minimal box that contains all colors appear in the image. Okay, so if we have 3 axes, green, red, and blue, then we can plot the actual colors in this 3D space. From our previous example, we have the tree, the blue sky, and a lot of snows. Then we can extract all colors and as a point in this 3D space. Okay, in this case, if the resolution of the image is 20 by 20, then we will have 400 black points in this 3D space. Okay, once we have pointed all these 400 points, then we can find a minimal box that contains all these black points. Okay, this helps us to determine what is the actual color, not over 17 million. Actually, we only have these 400 colors in the original image. Okay, that will be the first step. Step 2, divide the subspace containing existing colors into 2 to the power of b blocks of equal size. Okay, so visually we can do this. Once we have the box contains the original colors, just like this box, okay, then we can partition this box to 2 to the power of b blocks. For example, if our index color will be 2 by 2 by 2, okay, so that will be 8. So we can partition the box like this. Okay, so you can see for this case, we will have 8 different sub-blocks, which has equal size to the others. Okay. So in this case, once we can partition the original space into subspace, then we can represent each partition by the index color. Okay. So let's see for this example, once we need to reduce the color to 2 to the power of 8, then we can partition uniformly. For example, 2 to the power of 4 times 2 to the power of 2 to the power of 2. Okay, so eventually this equals 2 to the power of 8. Or you can also partition the original box to 2 to the power of 3, 2 to the power of 3, and 2 to the power of 2. That would also be 2 to the power of 8. Okay, so all right. So let's see. Once we can partition the original space, then we can give index to all these subspace. Okay, by 0, 1, 2, 3, 4 to 7. Once we partition to 8 different blocks. Okay, and then since it's uniform partitioning, so we can determine the range of the original colors. For example, the first one is 0 to 31, the next one is 32 to 63, because they have equal size of this partition. Okay, so let's see the drawback of this algorithm. Once we partition all the original color space into uniform blocks, it does not account for the fact that equal size partition of the color space may not equally populated. Okay, so this means from the original space, we have the distribution of the original colors. And then we use a box to contain all these colors. However, it may happen, for example, for this block, we have a lot of colors within this box. However, we may have only one color in this block. Okay, so in this case, you will see because we use only one colors to represent other colors within this block. For this one, we only use one colors to represent the actual color here. So it may not fair, okay? Because we have a lot of different colors, but they all quantize to one color of this block. But we only have one color in this block, and it can have the representation using these colors. Okay, so this will give us a lot of quantization errors because if we have a lot of colors in this range, then we hope we can partition to or maybe smaller blocks. Then we can represent this color accurately. Okay, otherwise, all these a lot of colors will quantize to only one colors. Then we will see the patchiness effects a lot, just like our previous example of cat. Okay, maybe we can see this example again. Okay, because you can see we have light gray, dark gray, and maybe white and black of this border of the cat. So that's will be the case. Once these colors are all in the color space here, then it will represent by only one colors. Okay, so maybe the results get worse because for these regions, we can use only one color to represent this area. Okay, so you will see even dramatic changes from this image to the original one, because we have very smooth changes of the original image. But once all colors are combined to at least sub-block using only one index color, then we will see more patches of the original image. Okay, so this brings us another algorithm, which is called median cut algorithm. Okay, so let's see the median cut. We may have non-uniform partition by this algorithm. Okay, so let's see the step. Firstly, to reduce the RGB color space to smallest block containing all colors in this image. So the first step is the same as our previous algorithm. Let's see the step 2. The algorithm proceeds by a stepwise partitioning at each step to produce some blocks contains 2 to the power of n, which equals c colors. So we need to divide by the in half along its longest dimension, such as c is divided by 2. Okay, so let's see this example. Okay, but we are not partitioning the original color space uniformly. So from the first step, we need to have a small box that contains all colors. Once we have such small box, then we can choose the longest dimension. So for this example, it's 2D. So we have the height and width. Okay, so we can see the width is the longest edge of this rectangle. Okay, so we choose the longest dimension and partition all colors from C to C divided by 2. Okay, so in this case, you can see how many colors we have for this example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So totally we have 22 different colors along the longest dimension. We just partition along this longest dimension and make these colors just half. Okay, so totally we have 22 colors. Once we partition here, then we can partition to 2 different partitions. Each contains 11 colors. Okay, and next, let's see. Once we have these 2 rectangles, then for the first rectangle, the longest dimension becomes this one, right? Because this dimension is shorter than this dimension. Okay, so we choose this dimension and have a cut that makes the color to half and half. In this case, we have 11 colors in this partition. So maybe the best partition will be 5 plus 6. Okay, so maybe we can have the partition like this. Okay, so we have 5 colors and 6 colors here. For this rectangle, this dimension is the longest one. So we partition here to make it 5 and 6. Okay, then we can proceed by this median cut algorithm again. Then until we have 2 to the power of b partitions. Okay, so in this case, you can see we have 1, 2, 3, 4, totally 8 different colors. That will be our 2 to our b with these colors. And then you can see from the results of the median cut algorithm, we have relatively equal size for each partition. Because for first partition, we have 3 colors. For the next partition, we have 3 colors, and 3 colors, and 2 colors. So it will be relatively averaged or uniformly distributed along all blocks. So this one is better than uniform partition of our previous algorithm. Okay, in the end, how to choose the quantized colors? we can just calculate the average of all colors in this block. For example, we have 3 colors in this block. So we just calculate the average of these 3 colors. So we use these colors as the quantized colors of this block. Okay, so every colors fall within this area will be represented by these red colors. Okay, so let's see the algorithm of median cut. Okay, the algorithm is very simple. For each pixel in the image with color C, we map C to RGB color space. Okay, and then we have a while loop here. Okay, so if L is the highest of B in this color space, then we split L into L1 and L2, and remove L from B and add L1, L2 instead. Okay, so B is our original RGB space, is the largest box in the first step. And then once we partition the blocks into L1 and L2, then we put L1, L2 into the set. That will be the target we need to process in the next step. And we remove L. Okay, so this is the while loop. Once B is not, if B is larger than 0, that means we have more blocks to process. Then we need to partition the space in this while loop. Okay, once we can partition all these subblocks and jump out of this while loop, then for all boxes in B, we assign a representative colors using the color centroid. Color centroid is usually calculated by the mean of all existing colors in this block. And then for each pixel of the space, we just replace the actual colors to the color centroid of all locations. Okay, so that will be the median cut algorithm. All right. Any problem of this algorithm? All right. So I would like to invite someone to summarize this algorithm for us. Why we need this algorithm and how to apply this algorithm.对对。嗯嗯嗯嗯嗯嗯嗯嗯嗯。Mm. Yes, because you can see for each block we have relatively equal numbers of colors within each block. Okay. So so when the partition ends, how to represent the original image? Mm. Mm. That's right. Very good. Thank you. 1 extra point. All right. Let's see. Do you have any other questions about these algorithms? Okay. If no question, let's take a break for 15 minutes.
Hi, our project is Dream Painter. We are artists, duo Barbara and Mar, and also scholars, Barbara Guliaeva from Hong Kong University of Science and Technology, Guangzhou campus.
And Mar Sola from Daniel University.
Here what you can see is the interpretation of our AI robotic installation of people's dreams. And it's, they are between figurative and abstract to leave the interpretation. So we don't really write down the text, what people were saying, but well, everyone can imagine. And the idea of the project Dream Painter is to understand or to ask if AI can understand our unconsciousness. So it's a bit of like in the Freudian line, right? So, and that's why it's also the Dream Painter. So is it painting a dream or our nightmare? Who knows? Explaining the interaction is that we use speech interaction method. So we like to work with this method because it feels for the audience magical, although maybe it doesn't sound really academic, but that's how it is. And the system understands what people say and translates to text, and then from text it goes to image, and image we rasterize to the lines, and then our robot Alfred starts to paint. And then, well, the interpretation or illustration, here is also kind of debate space, is then ready on the paper. And it's also kind of exciting to see what people are dreaming about. So we get pretty a lot of beaches and holidays, but also some nightmares. But we also kind of, the idea behind is that why we kind of like interaction method is also about like explainability of AI, because what is happening here, the audience are navigating in the latent space of clip. So you can actually see how the words, certain keywords in your text prompt, so to say, trigger the visual images, right? So it's actually the public can understand like what is behind of these AI models by experiencing this process.
Did you get the point of this video? Because I didn't, so I would like to see it twice.
Hi, our project is Dream Painter. We are artists, the duo Barbara and Mar, and also scholars, Barbara Guliaeva from Hong Kong University of Science and Technology, Guangzhou campus.
I am Mar from Tallinn University.
Here what you can see is the interpretation of our AI robotic installation of people's dreams. And it's, they are between figurative and abstract to leave the interpretation. So we don't really write down the text, what people were saying, but well, everyone can imagine. And the idea of the project Dream Painter is to understand or to ask if AI can understand our unconsciousness. So it's a bit of like in the Freudian line, right? So, and that's why it's also the Dream Painter. So is it painting a dream or our nightmare? Who knows? Explaining the interaction is that we use speech interaction method. So we like to work with this method because it feels for the audience magical, although maybe it doesn't sound really academic, but that's how it is. And the system understands what people say and translates to text, and then from text it goes to image, and image we rasterize to the lines, and then our robot Alfred starts to paint. And then, well, the interpretation or illustration, here is also kind of debate space, is then ready on the paper. And it's also kind of exciting to see what people are dreaming about. So we get pretty a lot of beaches and holidays, but also some nightmares. And yeah, but we also kind of, the idea behind is that why we kind of like interaction method is also about like explainability of AI, because what is happening here, the audience are navigating in the latent space of clip. So you can actually see how the words, certain keywords in your text prompt, so to say, trigger the visual images, right? So it's actually the public can understand like what is behind of these AI models by experiencing this process.
All right, is that clear enough? Anyone can summarize this technology for us? What did you hear? Okay, please.
From the speech to the text and input to the machine
Okay, so you're saying they can talk to the machine to transform the speech to text. So what happens when they get the text? Because you can see it becomes the artwork. It can be drawn by the AI robot, right?
It will transform to understand the text and transform it to an image.
That's right. Okay, so I'm not sure you have such experiences. You are talking about your dreams to your friends, and maybe they can imagine something visually. They can have a vision of what you are dreaming about. Okay, but here we have such technology can realize this process. If you talk to the microphone of this system, then your speech will transform to text directly. Okay, and then we have another technology to transform text to image. Okay, once your speech can transform to image, then the AI robot can draw the image by drawing its strokes. Okay, maybe the shape of these objects. Okay, that's something you can see on the wall.
Hi, our project is Dream Painter. We are artists, the duo Barbara and Mar, and also scholars, Barbara.
Okay, so you can see on the wall they have a lot of different paintings, such like random strokes or stroke of some objects. So that's the realization of the speech, how people describe their dreams. Okay, so are you familiar with the technology, how to transform speech to text and text to image?
I know that ChatGPT can do it.
ChatGPT can do what? Because we are talking about two different phases.
On a new release, I think that can support the whole
Process?
process.
Okay. For the first stage to transform the speech to text, this is pretty mature because when you use iPhone, we have Siri, right? So actually, when you talk to Siri, it transforms to the speech to text. And we also have some like open source project that help us to transform speech to text accurately, especially in English. So you can see a lot of YouTubers in Taiwan, they film their videos and they use such technology to produce the transcript below automatically. Okay, so such technology is pretty mature, but for the second stage, to transform the text to image, is still very academic. Okay, so we have a lot of different AI models to transform text to images and vice versa, because sometimes we can input the image and transform the image to the description of the text. So we call that captioning, image captioning, how to produce the text for such images. If we do it vice versa, then we input the text and according to the text or the description, we can generate the whole images. But you can see from this work, it's not the natural images. It just draw the strokes of the maybe contour of such objects. Okay, so it's just like a visualization method, how to visualize your dream. Okay, so I think it's pretty interesting, especially when you have nightmares. Okay, how to make it visual objects. What's that object? Okay. All right, let's jump to next algorithm. We call that arc-tree. Okay, so for arc-tree, according to this name, you can see we are building the tree structure, and for each node, we have 8 different child. Okay, so that can help us represent RGB values. Okay, so take this RGB for example. Once we have RGB channels for these 3 values, firstly we can transform to binary representation, such as 53, we can transform to 00110101. Okay, so once we have binary representation, then the next step is to consider the bits from left to right. Okay, so let's see the bits from left to right. The first bit is 0, 1, 1 for RGB. Okay, so 0, 1, 1. Actually, this value is 3. Okay, so this helps us to determine which child we are traveling from the roots to its child. Because each node has 8 different children. So from 0, 1, 1, we can see from the roots, firstly, we travel to children indexed by 3. Okay, and then we move to the next position. So it will be 0, 0, 1. Okay, so 0, 0, 1, actually its value is 1. Okay, so from this level to the next level, we travel from child 3 to next level, child 1. Okay, so if we move the step from left to right, we can have this representation. What is the child between these 8 children? We need to travel from its parents to this child. Okay, so if you consider this notation from left to right, actually we are traveling from child 3166 to the last child 7. Okay, so maybe you can imagine we have a complete arc tree. So if we have the root of the tree, it has 8 different children. Okay, and for each node, it has 8 different children. Okay, so you can imagine the arc tree. Once we have a complete arc tree, the tree is very large until the last level. Okay, however, if we can have 1 RGB values, actually we are traveling from the roots to the leaves node, just like from the roots, and we're visiting 3, and we're visiting 1, and then we can travel by this complete arc tree until we reach the leaf node of the tree. Okay, so this is a very simple example how we travel arc tree by the representation of different RGB values. Okay, next let's see how we select 2 to the power of B index color. Okay, so let's see more detail on this arc tree. So once we have our predefined value 2 to the of B, we need to choose such number of colors. Then we will apply from the okay, so if this is the original image, for example, the resolution is 20 by 20. Okay, then we will start from the first pixel. Okay, so the first pixel, it has its own RGB values, just like our previous example. Then we can travel from the first pixel and trace the arc tree to see where it ends. Okay, and then we jump to next pixel. Okay, so for next pixel, maybe we travel to different paths of the tree. Then we reach a leaf node. In this case, we already have 2 colors in the total number of 2 to the power of b colors. Now we have 2 colors. So if we are lucky, then when we travel, if this number is 8, pick 8 for example, if we travel first 8 pixels, then maybe we have different destination of different leaves. Okay, then what happened if the number we already have 8 pixels? So what happened to the pixel 9? Okay, because we only need 8 different index colors. So once we have the next color, the pixel index is 9, then it will follow the arbitrary algorithm to reach some leaves. But we couldn't include that new pixels into 8 colors because the maximum number of index color is 8. Instead, we will merge these colors to the nearest colors of the tree. Okay, so in that case, when we travel, for example, this pixel, we travel the tree and we locate it at this location. So maybe its closest color of these 8 colors is this one. Okay, so we merge these 2 colors to calculate its average colors as our index colors. So next, we use the scan order to scan the original images and merge the new colors to the existing 8 colors in the arc tree. So when we travel to the next pixel, then in the end, from this arc tree, we can choose the final 8 index colors. Okay. Is this clear enough? All right. So that's all about the algorithm, how we choose index colors for this algorithm. Because for the first step of index colors, we need to determine the range of the actual colors. And then for step 2, we need to choose 2 to the power of b index colors. And for the third step, we need to map the actual color to the index color. So we are talking about all the algorithms for step 2, how we choose index colors. So we have popularity algorithm, we have uniform partitioning algorithm, we have median cut, and we have arbitrary algorithm to help us determine what are those 2 to b index color. Okay, any question for this part? Okay, if no question, we will jump to next topic, deferring. Okay, I believe you have very rare chance to see these keywords deferring in your daily life because it's very specific for image processing. Okay, it's a technique to simulate colors that are available in a palette, but we can simulate that color using available colors in our palette. For example, if in our palette we only have red and blue colors, okay, that's all the colors we're allowed to use. But by different spatial arrangement, for example, it's just like a chessboard. We partition the space of the images into 2 different like chessboard patterns. For example, red, blue, red, blue, red, blue, red, blue. Okay, so in the end, we may have some image like this. So it looks like purple, right? Okay, so that's one technique. Even we don't have the color purple, but due to this very spatial arrangement, then we can simulate the color pupil by increment the position of red and blue. Then visually, we may see the color pupil. Okay, so that's the technology of deferring. So can anyone summarize deferring in Chinese? For example, one or two sentences for us? Okay.嗯。Okay, good. Okay, so let's see during effects. Okay, so we have seen index color, right? So if this is the original image, once we apply index colors, we can see visually artifacts, these patches of different colors. However, if we can apply the serving method, okay, then you can see the artifacts is significantly reduced. Okay, because we have very spatial arrangement of these colors, so that makes we have visually additional colors, so we won't have such patchiness of the artifacts from index color. Okay, so let's see different algorithm of deserving. Actually, we can apply deserving to increase more colors visually. However, if we go back to grayscale images, we can like simulate grayscale levels by deserving method. Okay, so the first method is called thresholding. Once we have the grayscale images, we can change the pixel value. Once we have a predefined threshold, for example, 128. Okay, so you can see this is the median of the grayscale range from 0 to 255. Okay, so if we have the pixel value larger than the threshold, then we make it white. Otherwise, we make it black. Okay, so in this end, we can create a binary image. So that's the results after thresholding. Once we convert the grayscale images using a predefined threshold, then we can represent this image with only black and white pixels. Okay, but you can see the results looks like worse because we have dot here. After thresholding, we lose the shape of this dot, only a lot of patch of white and black. Okay, so next let's see how we apply the deserving method to reduce the artifacts of thresholding. So the first method is called noise deserving. Okay, so let's see. Noise deserving, the algorithm is to generate a random number from 0 to 255 at each step. Okay, then we can apply the linear scan order for each pixel. Then we can examine if the pixel's color is greater than this random threshold. If it's greater than, then we make it white. Otherwise, we make it black. Okay, and we repeat the step for each pixel. Okay, so for thresholding method, the threshold is fixed to 128. But for noise deserving, we have a very dynamic threshold for each pixel. Because for the first pixel, maybe our threshold will be a random number. Maybe the random number will be 200. So we will see if this value is greater than 200 or not. Then we make it black or white. For the next pixel, then we have another random number. Maybe it's 10. Okay, so we can see if this number is greater or less than 10, then we choose to make it black or white. Okay, so for each pixels, we randomly choose its threshold. So in the end, we may have the result like this. Okay, so if for thresholding method, we will see a lot of patchiness. But if we apply noise deserving, we may see something like this. Okay, so if the student sitting behind the classroom and watch this video in a very long distance, maybe you will see relatively good grayscale image. But if you watch it closely, of course, it looks very bad. You have a lot of like black and white noises of these images. But if you watch this at the long distance, then the results looks pretty reasonable. Okay, so let's see the concept of noise discerning. Actually, it eliminates the patchiness by adding high frequency noises. Okay, so I would like to invite someone to explain why we won't have patchiness artifacts if we apply noise discerning. Because from the results you can see, we don't have a lot of black or white edges. Compared to thresholding method. Why we can eliminate such patchiness artifacts? Any idea? But why it will have the results like this? Why it won't have the whole patch of black or white? Okay.
是变成几率性的问题。因为白色的地方就是白色的地方选到可能一个大的值的几率很大，可是就这一片会被视为是白色的那个几率就会比较大，所以即便说它有那个灰点，可是多数人还是会转换成是白色的。
But it also has a chance to be black because we have dynamic threshold here. Okay, if we choose a very high threshold, for example, it's so bad luck. The threshold is 255. So once we have a very high number, 240, it's still below the threshold to be black. So it's all random. So that's the mechanism you are mentioning, because we have a random mechanism. Okay. Okay, next let's see another method, average discerning. We calculate an average pixel value. If the pixel value is above the value, then set to white, otherwise set to black. Okay, so you can see this provides a little bit improvement of the thresholding method. We are not using the median number. Instead, we choose the average pixel value as our threshold. Okay, so this is the results of average discerning. Okay, next let's see pattern discerning. It's also called order discerning or Bayer method. Okay, we break this image to small blocks and we define a threshold matrix for each position. So we use different threshold for each pixel of the blocks and compare the grayscale values to the threshold, and then we turn it black or white. Okay, so let's see this example. If this is a 3x3 image block, so we have its original grayscale values. For these white pixels, the grayscale is 255. For these dark gray pixels, the grayscale is 128. Okay. And then we can define a threshold matrix 3 by 3 for every block. Okay, so if the threshold matrix looks like this, okay, this is a predefined threshold matrix. Then we can compare each corresponding positions to see it's above the threshold or not. Okay, so let's see for first location, 255, and its threshold is 200. So the value is above the threshold, so we give it white. Okay, and then for the second position, 192, the threshold is 250. Okay, so you can see this value is below the threshold, so we make it black. So in the end, we may have functions like this. Okay, 1 means white, 0 means black. So we have the results like this. Originally, it looked like this, but after pattern discerning, okay, so we have the results like this. Okay, so you can see for pattern discerning, we have the results like this. Okay, just like a little bit chessboard, black and white, black and white. But if you watch it in a long distance, you will see this looks actually very good. So I believe you can see a lot of advertisements on the wall of the bus. Okay, so if you see the advertisement on the wall of the bus, it's usually applied pattern discerning. Okay, so have you discovered the trick of pattern discerning, how to achieve such results like a chessboard, but it's also a mixture of high grayscale and low grayscale to mix a new grayscale value. Okay, why the result looks like a pattern, like a chessboard? Have you discovered the secret? Okay.
那个 threshold 太去，去特别设计它的那个阈值就不一样。
So how to define the threshold matrix to make it like a chessboard? Your direction is correct. How to make it look like a chessboard pattern? Just one step away to the correct answer. All right, maybe you can see from the results we have white, black, white, black, white, and black. So how to make it a chessboard pattern? Okay, maybe you can see the corresponding position of these 4 positions. And you can see its threshold is relatively high, 250, 220, 200, and 150. And for these 5 positions, you can see its threshold is relatively low, right? So it's easy to above the threshold if the threshold is set to 10 or 15 or 100. Okay, so for these positions, it becomes white easily, and for these positions, it becomes black easily. Okay, once we define the threshold matrix, just like we have high values for these 4 positions and relatively low values for these 5 positions, then we can make the final result look like a chessboard. Okay, next one is called error diffusion deterring. It's also called Floyd-Sternberger algorithm. I remember when we had this test in midterm examination to ask you to apply Floyd-Sternberger algorithm, a lot of students cannot answer and leave the answer blank because they only know the name error diffusion deterring and they forgot the name Floyd-Sternberger. It looks so strange to them. Okay, so I hope you can understand this name. Maybe for the midterm examination, you will see this name again. Okay, so let's see the concept of error diffusion method. Actually, we distribute the errors from one pixel to other positions. Okay, so let's see this method. First thing is to define the mask. Okay, so we have the pixel P, for example, and we only consider the position to the left and to the bottom. Okay, so we didn't consider the location in the left-hand side of P. We only consider the location 7, 5, 3, and 1. These 4 locations. Okay, then for each pixel P, we define the error E. Okay, so if P is less than 128, then we define the error E equals P. Otherwise, the error E equals P minus 255. Okay, so maybe I can give you a quick example. Once we have the original image, so maybe if P is 200, then the neighboring pixel, for example, 100, 10, 50, and 255. Okay, so this is the original image. Then for the position P, okay, so P is larger than 128, right? So error equals P minus 255. 200 minus 255. In this case, our error will be minus 55. Okay, and then once we calculate the error E, then we change the value of its neighboring pixels. Okay, so once we have E equals to minus 255, we just give different quotient and add this error to the neighboring pixels. For example, we have 7 divided by 16 times E and add this value to the position here. Okay, so in this case, we have minus 55 times 7 divided by 16. This is the error we want to diffuse to the neighboring pixels. And the pixels is 100, so we add 100. So this one is called error diffused to neighboring pixels. Okay, so maybe it's just like half of minus 55. So maybe it's something like minus 27 plus 100. So in this case, the value of 100 becomes 73. Okay, so that's how we diffuse error messages to neighboring pixels. Okay, so you can apply this method to 3 other locations, 10, 50, or 255. Once it's at these errors of different ratios, then the grayscale value changes after error diffusion is earned. Okay, so the algorithm is very easy. So maybe the first thing is why we have such spatial ratio of this. For example, 7 divided by 16, 3 divided by 16. So actually, if you add that all together, you will have 7 plus 3 plus 5 plus 1. The total is 16. Okay, so it's just like a normalization. We just partition all errors to 16 different parts. And we have 7 divided by 16. the largest part to the right neighbors. Okay, and we have the least amount 1 divided by 16 of E to these neighbors. Okay, so you can see according to the spatial positions to location P, we have different portion to distribute the errors to its neighboring pixels. Okay, so this is the algorithm of error diffusion deserving, and we can see the results. Once we have the original image after the deserving, we may have the image like this. Okay, next I would like to think about why this algorithm works. How to achieve the goal of deserving once we can diffuse errors to the neighboring pixels. Okay, so maybe we can see another case. Then you might have the feeling why this calculation achieves deserving results. Okay, so let's have the second example. Okay, so if our grayscale value of P is 10, okay, and then maybe we have 20, 30, 40, and 50. Okay, let's see what happened once our image looks like this. Okay, for each pixel P, now P, the grayscale is 10. Then first step is to define the error E. Okay, so in this case, 10 is less than 128. Okay, so E equals P equals 10. In this case, our error is the pixel value 10. All right, and then we diffuse the error to neighboring pixels. For example, for the pixel 20, then our error will be 7 divided by 16 times 10 plus 20. Okay, and then this location, its value becomes 7 divided by 16. So it's like 4 point something plus 20. Let's make it 24. Okay, so this value becomes 24 after error diffusion. Okay, so compare this example to our previous example. Have you discovered the secret why this method can achieve deserving effects? Two extra points. Okay.
是它会把四周的格子变成像是那个像机器人那样，就是说，假如中间那个是比较小的数字，那它就会那个算出来应该是正，所以它会把它四周的加上那个数字，让它方面会比较大，所以它就是中间喜欢旁边大，它们就类似那个起来。还有它比较 P 大的话，那算出来的 E 就是负的。
Error E will be negative value. And then
那这样子，它就会把旁边的那个数字减小，这样看起来就是中间会是大，然后会小。
Okay, very good. Why are you so smart? Very correct answer. If you watch the definition of error, that makes the effects. If we have dark values, then the error will be positive. You will add positive numbers to neighboring pixels to make neighboring pixels even brighter. Okay, so that achieves the effects of chessboard. If we have black in the center, then all the other surrounding pixels will become white. Okay. On the contrary, if we have white value as p, then we will have negative error, because if p is 200, then error will be p minus 1255. So we will diffuse negative values to its neighboring pixels. So if this p is a bright pixel, 200, then once we put negative values to neighboring pixels, all neighboring pixels becomes darker. Okay, so that achieves the goal of chessboard: black, white, black, white, black, white. Okay, very good. 2 extra points. All right, so maybe you can apply this method to color images, because we are talking about all these algorithms for grayscale images, how to adjust the grayscale value to achieve the desired results. Once you can mix different grayscales, maybe visually you will see new grayscale values. So similarly, you can apply this algorithm to color images. Okay, once you put different colors as neighboring pixels, maybe after the mixture, you will visually see new colors of this image. Okay, that's all about the deferring method. Any question for this part? Can we repeat it in Chinese? OK， 同学看起来都好木讷哦，好，就是都没什么反应哦，这都不太确定大家是不是真的有听得懂哦。好，好 ，If you have any feedback, you can talk to me anytime. Okay. Okay. Next, I would like to introduce the method image transformation, because it's applied in a very wide range of applications for image processing. If you open Photoshop, you can see a lot of different artifacts, spatial effects, so you can apply for the images. Actually, in the back, we have such technologies, image transformation behind these spatial effects. Okay, so simply speaking, we can say, what is image transformation? We have a very special process to change the color or grayscale of the image pixels to create different, for example, atmosphere of these images. Okay. We have 2 different categories of method. The first one is pixel point processing. So we can define very spatial transformation function for each pixel to transform the pixel value to different values. Okay. The second method is spatial filtering. We change the pixel's value based on a bunch of neighboring pixels. Okay. So we call that spatial filtering. Let's see the first category of the method. So the first important method is histogram. So histogram is a discrete function that describes the frequency or number of occurrence of each colors. Okay, so maybe we can see the example directly. This is a very simple histogram. If we have a group of 32 students in our class, then we can actually calculate different categories. For example, 1 for freshman, 2 for sophomore, 3 for junior, and 4 for senior. Okay, then we can actually count the number of each category. Then we can draw the histogram. So for the x-axis, we call this beam, a different category, but we have the keyword beams for histogram. The first beam, freshman, second beam, sophomore, and junior and senior. And we have, for example, 10 students for freshman, and we have 6 students of sophomore. And we can plot the histogram of the distribution of these 4 categories. All right. Then we can apply the histogram concept to color or grayscale images. Once we change the beam to different grayscale values, for example, 0, 1, 2, 3, 4 to 255, then we can count the number of pixels, how many pixels of grayscale value 0 in this image. Okay, and then we can plot the histogram or the grayscale distribution for this image, just like this. Okay, so take this image for example. We can calculate the histogram from 0, 1, 2, 3, 4 to 255. So in this case, you can see we have no black, we have no white pixels. Instead, we have a lot of pixels in the middle part of this spectrum. Okay, so actually we have a peak here and another peak here. So you can reflect to the original images. Maybe some grayscale is the flower, another grayscale is the background. Okay, so based on the histogram distribution, maybe you can guess or imagine what this image looks like. Maybe we have two major grayscale of pixels of this image. All right, then based on the histogram representation, we can calculate the mean or average or median of this histogram. And we can also calculate the standard deviation if we use each xi minus the mean x bar, then we can calculate the standard deviation sigma. Okay, so simply speaking, histogram is just like the distribution of all possible categories. Next one is luminous histogram. Okay, so if you remember, we can transform RGB color model to the representation of luminous components by this equation. So this is in 2, if you remember. So once we have a color images, we can transform all RGB channels to the representation of luminous components. And then once we have these luminous components, we can draw a histogram based on this luminous component. We call this a luminous histogram. Okay, so histogram is not just like a statistics of these images. Actually, we can apply different image processing methods based on histogram. So, okay, so one method is called histogram stretching. If we have low contrast of the images, then maybe we can stretch the histogram to like it spread over the whole spectrum of the histogram, just like this. Okay, so we can see in the original image, the histogram most appear in the range in the middle area of this spectrum. However, we can apply the algorithm like to spread the distribution over the whole spectrum. So after that, we may have some more pixels of black and white, and to increase the contrast of the original image. I wouldn't introduce this method because maybe you can see this method in image processing provided by Professor Liu Xingzhang. Okay, so if you are interested, you can participate in the image processing course. Okay, next let's see the transformation function. Okay, we call that pixel-based processing because once we can define the transformation function t, then we put each pixel value f of xy into this function, and we can get another transform grayscale value p2. So if you put p1 into this function, after the transformation function, we can get another value p2. Then we actually transform each pixel to a new pixel value. So that's the reason we call that pixel processing transformation. Okay, so we have a very simple example of such transformation function. The first one, we call that identity transformation. That means we didn't change the value. So after the transformation, the value remains the same. So you can see this is a straight line. The angle is 45. Actually, 0 transform to 0, 1 transform to 1, 2 transform to 2. So if you put different pixel values into this identity function, then actually we did nothing about the pixel value. Okay, so based on this identity function, maybe we can translate the function a little bit. For example, we move this straight line up here. Okay, if we translate the images, for example, 5 pixels above, then we can see for the pixel 0, it transforms to 5. 1 transforms to 6. 2 transforms to 7. Okay, so in the end, what did we do for this transformation function? If we transform 0 to 5, 1 to 2, 1 to 6, and 2 to 7, we are actually increase the brightness of the grayscale images. Okay, so based on this transformation function, we are trying to increase the brightness of this grayscale images. Okay, on the contrary, we may have the transformation function like this. Okay, if 5 transform to 0, and 6 transform to 1, and 7 transform to 2, then we are decrease the brightness of these grayscale images. Okay, so a very simple example to help you understand what kind of transformation function we may have. Okay, next let's see another 3 transformation function. For this one, let's see what happens for this transformation function. 0 becomes 255, and 255 becomes 0. Okay, so it's achieved the result of inversion. So black pixels becomes white pixels becomes black. Okay, we just inverse the grayscale of these images. Okay, secondly, we have the transformation function E. So it's like a threshold, right? We have this threshold. If the grayscale value is below the threshold, it becomes 0. Otherwise, it becomes 255. So we are trying to create a binary image, only black and white pixels. Okay. The last one is very interesting because you can see the shape of the transformation function is a very smooth, continuous H-shaped function. So what does it do? Okay, if we compare this H-shaped function with the identity function, okay, so if this is the identity function, we know the angle is 55. Okay, it's a straight line. Okay, I didn't draw it very well. Okay, but I can consider this is the identity function. Then let's see what happens for this H-shaped function. And if you consider this is the middle point from 0 to 255, so maybe this point is 128. Okay, so you can see for the darker values from 0 to 128, the value becomes smaller. Okay, and for brighter pixels, for the range to 128 to 255, the value becomes even brighter. Okay, so this helps us to increase the contrast of the original images. Because for dark pixels, it becomes even dark. For bright pixels, it becomes even brighter. Okay, so this helps to increase the contrast of the original image. Maybe we can see the examples once we apply this transformation function. So if this is the original values, we have seen when we draw the histogram, we have 2 main peaks of this. For example, we have light gray or dark gray for we have the most occurrence of such pixels. If we apply lightening, then you can see the total brightness of this image is increased. So if we darken these images, then the total grayscale is decreased. Okay. And then we have inversion, and we have thresholding to make binary images. And then for the H-shaped images, we increase the contrast. So you can see, compare this one to this one, we can see more details and more grayscales after increasing the contrast. Okay, so basically we are talking about very simple transformation functions we can apply to each pixels to change its grayscale values. Next, let's see a very famous transformation function, which is called gamma transformation, because you can see this function in your LCD monitors. If you open the display, and actually you can apply gamma transformation that help you to adjust the colors of your new LCD monitors. Okay, so let's see this equation. We have a gamma value. Gamma is an exponential that defines a nonlinear relationships between the input level R and the output level S. Okay, so this equation is very simple. The original grayscale value R after transformation S. Okay, so we are setting the gamma value as the power of the original value R. Here, R and S is normalized to the range of 0 and 1. So we are not using 255 anymore. All values is divided by 255 to normalize to the range 0 to 1. Okay. Next, let's see what the effects of different gamma value. Okay. So if gamma is equal to 1, then you can see S equals R. We have no changes. So we can see the transformation function is just the straight line of 45 degrees, the identity function. It did nothing. Okay. But once we increase the gamma values to 1.5, 2.5, or 5, or 10, or 25, you can see we are trying to like skew these lines. Okay. Okay, so can you imagine what happened once we apply this line? For example, gamma equals 2.5. Or if we set gamma below 0, for example 0.4, we have the curve like this. Okay, so if you compare to the identity function for the 45 degree straight line, then you can see actually we are making all grayscale values to a darker values. Okay, because for 2 that becomes 1, for 3 that becomes 2.5 or something. So every grayscale value, if we use the transformation function gamma larger than 1, then every grayscale value becomes even dark. Okay. So when gamma is set to values less than 1, then we make every grayscale value even brighter. This is the example of gamma transformation. So we have the original value here, and then we set gamma to 3, 4, and 5. Okay, so based on the previous discussion, you can see if the gamma value is larger than 1, actually we are darken the original images. So basically the results when gamma is set to 3, 4, and 5. So we can compare these three cases. You can see when gamma is set to 5, we have the darkness images of all these three processing results. All right. So that's the end of pixel processing method. Pixel point processing. Okay. So actually, we just defined the transformation function then you can make each pixel values as the input and then adjust the value based on the given transformation function. All right, any question for this part? All right, if no question, I'll see you next week, or you can come forward to discuss with me.
有加入到去的。